Okay, hi again, everyone. Welcome back to the last talk of today before the reception. So today we'll have another talk on the lower bounds of metropolized sampling methods for well-conditioned distributions. And this is by Kevin Tian, who's a PhD student at Stanford, a student with Aaron Sidford. So Kevin, please.
Oh, great. Hopefully the mic works okay. Yeah, thanks everyone for coming to my talk. I'm a grad student at Stanford, and this is joint work with Yintat Li and Ruoqi Shen, who are awesome collaborators from the University of Washington. And the talk will be about lower bounds on metropolized sampling methods for well-conditioned distribution. So it's a interesting follow-up to Sinho's talk. Okay, so diving straight into it. So a major research goal of computational sampling, and this program, I guess, in particular, is understanding the oracle complexity of sampling. So here we want to sample from a density whose negative log density is convex, and it's in high dimensions, so for large D. Okay, so this talk is going to focus on the well-conditioned regime in particular, and I'm going to try to motivate this a little bit. So in particular, when I say oracle complexity, usually we assume that we can interact with the density through some manner of oracle, and a natural one is derivative oracles, where at a point I can query say the value or the value of some derivatives of the function. Okay, and under these kind of oracle axis, it's natural to assume regularity assumptions on the derivatives of the function, and the well-conditioned regime is in some sense the minimal sort of assumption you can make. Okay, this is not quite true, but hopefully you'll forgive me for this motivation slide. Okay, and as Sinho mentioned in his talk, sort of the overarching goal here is to develop an analogy to the oracle complexity of optimization, which is quite well understood in the well-conditioned case. And there are many interesting connections between sampling and optimization, some formal, some informal. Let's just say that it's been a great success story in optimization, and we'd like to get something similar for the sampling setting. Okay, so formally the well-conditioned regime we're going to study in this talk is as follows. So the goal is to design a sampler to produce a sample within epsilon total variation distance from the target distribution pi. And the regularity assumptions we're going to make on pi is that its Hessian is pointwise bounded between multiples of the identity, so mu and L. So here mu is say larger than 0, and L is smaller than infinity. And this condition number kappa, which is this like L over mu ratio, we're going to assume is finite. So this is what I call the well-conditioned regime. Okay, and finally, we're going to be working under the following oracle model, where at a point you can query either f of x or the gradient of the function at that point. Okay, so this is sort of like the setup. We're trying to understand the oracle complexity of this sampling task. Great. So diving a little bit into the types of methods that people study, there's sort of two classical regimes in the recent literature. One is the low accuracy regime, where the sampler has a polynomial dependence on this target parameter epsilon. And it's typically given through guarantees in various distance metrics, including total variation, as I described, but also various other ones, such as Wallacean distance, KL divergence, and so on. And there have been a variety of discretization tools and like analyses and like base dynamics that have been studied. I won't go into it too much, but suffice to say this regime is very rich. Okay, but this is not the focus of today's talk. Today's talk is going to focus on the high accuracy regime, where we want to design samplers with polylogarithmic dependence on the target accuracy epsilon. Okay, so the key difficulty in attaining such rates is reducing the bias of the sampler. So in particular, most of these like low accuracy regime samplers have a biased target distribution. And to fix this problem, typically we use Metropolis adjusted algorithms to correct for the stationary distribution. So this is like a general tool that takes any proposal and fixes it so that the stationary distribution is correct. Okay, and finally, I'll mention that most results in the high accuracy regime give guarantees in total variation distance. And the main high accuracy algorithms that people study in the literature, and often these algorithms inspire what's actually used in practice, are the Metropolis adjusted Langevin algorithm, or MALA, and Metropolized HMC, Hamiltonian Monte Carlo. And this talk is going to focus on giving lower bounds on the complexity of using MALA and Metropolized HMC for the sampling task I mentioned on the previous slide. Okay, great. So when I first tell people about this results, it's always like a little bit disappointing because, you know, an easy counter is, okay, you didn't really say anything about the complexity of sampling if you're like proving algorithm-specific lower bounds. Okay, so that's like maybe a little bit sad. So let's look on the bright side. So on the bright side, I know how to prove a result. So, you know, that's one upside. Maybe a few other upsides are that I can use this algorithm-specific lower bound from an algorithm design standpoint to pinpoint difficulties in the algorithms that I have to like sort of overcome in order to obtain better dimension dependencies or other dependencies. And finally, the candidate hard distributions I specify for these particular algorithms might have some like nice general properties that you can exploit in further lower bound design. Okay, so these are a few upsides. Now, if it sounds to you like I'm just making a bunch of excuses, that's fair. And I think a major goal of this field is to prove like, you know, algorithm agnostic lower bounds in high dimensions. So let's try to do that. Okay. Okay, but you know, charting forward, because this is the results I know how to prove. I'll survey the types of lower bounds that we give in this work. So the first pair of results I'm going to state. So these are direct copy paste from the paper, but let me try to break down what the statements are. So first of all, these two theorems are lower bounds against Mala. So this is a one parameter family of algorithms, which is specified by just a step size. So basically, if I give you oracle access to a density, then the only thing Mala gets to choose is the step size. So in that sense, it's one parameter. Okay, and I'm making this distinction between Gaussians and general well-conditioned densities, where a Gaussian is required to have a constant Hessian. So namely, its negative log density is like a quadratic. Okay. Furthermore, I'm fixing the scale of the problem in these theorem statements, where I guarantee that not only is the ratio of the eigenvalues bounds kappa, I'm telling you up front it's between 1 and kappa. So it turns out that this only makes our life harder in terms of proving lower bounds. And otherwise, the problem is a bit silly because if you fix the step size first and then I fix the scale, I can sort of like cheat my scale to make your step size like absurdly large. And then your chain sort of can't do anything. So this is sort of a natural assumption. Okay, and finally, theorems 1 and 2 give relaxation time lower bounds. So relaxation time is this spectral notion of mixing. In particular, it's defined as the inverse spectral gap of this transition operator. So there's like a formal definition here, but you can basically think it's a way to measure the rate of decay of any function which is orthogonal to the stationary distribution. So it's just saying like how quickly does this like transition operator kill off orthogonal functions. Okay. So yeah, that's sort of like a breakdown of what these theorems are really saying. Okay, so just to, yes.
What is your job here when you said makes our job harder? You mean your job of proving lower bounds?
Proving lower bounds, yeah. So like,
why does it make it harder? I'm confused.
So there's two different ways I could have stated this. I could have said, first, you tell me a step size, and then I get to pick a function, right? Alternatively, I could say, first, I pick a function, like namely a scale, and then you pick a step size, right? I'm just pointing out that the first alternative is a bit silly because if you pick a step size first, I can cheat the scale to make it like your step size not make sense.
I understand. Isn't the statement picking the step size first? I'm super confused.
Oh, I'm saying I'm fixing the scale as 1 kappa. The statement includes the scale.
I see. Okay.
Yeah. Okay. So just to address Philippe's question in a cartoon, sort of the thing you should think about is nature or like whoever gave us the problem picks both the dimension and the scale of the problem, like 1 kappa, and then like the bad guy, like the upper bound algorithm, gets to pick the parameters, and then we get to pick a hard function or starting set or whatever to try to like combat your algorithm. Okay. So recapping a little bit from Sinho's talk, I want to like clarify the context of our lower bounds with the upper bounds that are known in the literature. So Sinho's talk described the following picture. If you have a feasible exponentially warm start, so namely like a start I can just like tell you off right off the bat, then the mixing time of Mala is roughly kappa d. Okay, but if I promise you have a polynomially warm start, then you can actually improve this to kappa root d. Okay, and here's the definition of warmness. It's sort of like this worst case ratio between starting and target distributions. Okay, so you might stare at these theorems, lower bound theorem statements a little bit, and these upper bound statements, and be like, okay, what gives? First of all, your lower bounds are in terms of relaxation times, and these upper bounds are in terms of more classical mixing times. Okay, second of all, your lower bounds said nothing about the warmness of the starting set, right? They were purely like spectral statements. So how do we get around this? So our third theorem is a mixing time lower bound for Mala. So in particular, we say that you can upgrade theorem 2 to say, okay, in fact, it takes this many iterations from a exponentially small measure set to reach constant total variation from the target. So I want to clarify a few things in this statement. So if I ignore the statement about warmness and I just read the number of iterations required to reach constant total variation distance, this is sort of like the standard combinatorial mixing time definition. You can imagine you're trying to prove some bound on mixing time of a graph. It's over the worst starting vertex, something like that. Okay, but in continuous time, this is sort of hard to accomplish because you can imagine my starting distribution is just way out there in space and sort of it'll just take forever to do anything, right? So we give a slightly more refined notion of a lower bound, which is warmness sensitive. So the way you should think of this is first I get to it's an infimum over algorithm parameters, and then I get to choose the worst warm start of a given warmness, and then we try to lower bound this quantity. Okay. So I'll mention that this sort of lower bound, while it seems like a little bit easier to prove because I get to literally choose the starting distribution, it's actually compatible with most continuous mixing time analyses, which only depend on the starting distribution through this warmness parameter. So, if you want to navigate around this this lower bound, you're gonna have to come up with some new upper bound machinery. So I think this is a reasonable warmness sensitive lower bound. Yes.
I'm a bit confused by the statement. Isn't the supreme also be over the potentials or the density?
Yeah, the supremum is also over functions satisfying the parameter. I'm just highlighting that I get to choose the warm start after you choose the parameters.
So your supremum, the second supremum she just referred to, should be after your hints, right?
Sorry. I think the comment is just that the supremum is actually over more things. It's also over the potential, which gets to respond to the.
I'm asking if before or after the supremum over.
I thought you said you first pick your steps.
Oh yeah, sorry. Yes, right. Good point.
Actually, while we are on this, can you mention the harder even task of I give you a specific distribution, you can prove a lower bound on the, is this possible to actually get similar rates if I actually allow you to first look at the distribution, force you to use Mala and select your step size after you look at the distribution?
Yeah, it's a good question. You're basically saying you can pick the best step size for your particular distribution or something like that. Yeah, I haven't thought too much about that. That I agree is important and perhaps more challenging. Likely more challenging. Okay.
Yeah, so I have a question.
Oh yes.
So in some sense, you can always try to match your initial condition so that it's not too bad or it's very far away from your soup of beta warm start. I think that's.
You're saying my definition doesn't rule out just literally starting at the target distribution or something like that, right?
No. I don't mean you start with the target distribution because you don't know that. But what you can do is you try to fit something easier. For example, you look at the shape and say some Gaussian may be much better than the initial condition that has soup form.
Right. So I agree. This sort of statement doesn't rule out upper bounds as you're describing that. Take advantage of the fact that I know more about the warmness the starting distribution other than the warmness. I'm just pointing out that if your analysis only actually depends on the starting distribution's warmness, then this lower bound rules out your analysis. But I agree you can take more advantage of the warmness, the warm start that I'm telling you.
Thank you.
Yeah. Okay, great. Are there any more questions? Because this is sort of a key definition. Okay, great. So our second set of results are about HMC. which is sort of a multi-step generalization of Mala. So we give like two types of statements about HMC. So the first is an unconditional spectral lower bound, and it has the following flavor. If you take k-step HMC, then the relaxation time can only decay by a factor of roughly k, up to this fact that there's a square root d in the numerator rather than a d. Okay, so if you've never seen HMC before, basically you should think that each HMC iterate takes k steps of some like integrator like subroutine. But the point is, in every iteration of HMC, it requires k gradient queries. So roughly speaking, if you improve the mixing time by a factor of k, then you sort of like evened out because you need k gradient queries per iteration. So theorem 4 basically says if you're willing to ignore differences between relaxation time and mixing time, sort of there's an inherent dimension dependence in HMC. You can't beat this sort of root d barrier. Okay. So we also have like some mixing time lower bounds for HMC, which are a little bit weaker in the sense that they only work in certain regimes of this k parameter. So the statement is as follows. For small enough k, so small enough here means like k is less than some polynomial in d. We didn't try very hard to optimize it, but like think like k is less than d to the 1/10 or so. You can only decrease the mixing time of HMC from like theorem 2 or theorem 3 or like Mahler result by a factor of roughly k squared. So this implies that the query complexity can improve, but it can only improve by a factor of roughly k. So my takeaway from this is if you want to beat the mixing time of Mala by more than a like a polynomial factor in the dimension, you have to take polynomially many steps. That's sort of like the conceptual message in these sorts of results. Okay. And these are all from exponentially warm starts, just like our Mala results. Okay. So just to summarize the last few slides, our first set of results are on Mala, and we have kappa root d spectral lower bounds for Gaussians and kappa d mixing time lower bounds for well-conditioned distributions. On the other hand, for HMC, we have these sort of like incomparable results. We have kappa root d over k type lower bounds in the spectral sense, and we have kappa root d over k squared type results in the mixing time sense. So it's an interesting open question to like improve either of these. Okay, so for the rest of this talk, I'm going to first define the two algorithms we're going to study. Then I'm going to sketch the proof of theorem 2. This is sort of like our main like technical result, which says like the kappa d spectral like lower bound. Then I'm going to give a proof sketch of theorems 3 and 4, which are like the mixing time lower bound and the HMC spectral lower bound. And then I'll give some like parting thoughts on like things I think would be exciting to work on and things our paper suggests for practitioners and lower bound theorists and things like that. Yeah. So the first algorithm we're going to study is Mala. So Sinho already defined this. I'm just going to like rush through this a little bit. The idea is it's going to like apply a filter to the Euler discretization of Langevin dynamics. So the proposal distribution from a point x is you're just going to advance for time h by the gradient, and then you're going to like draw a Gaussian around it. And then the actual algorithm is to just apply like a Metropolized filter on top of this. Okay. Yeah, I won't say too much about this other than the one parameter is h, like how long you discretize for. Okay. The second family of algorithms we study is multi-step HMC. So you should think the base like continuous time process that's being discretized here is the Hamiltonian dynamics, which are defined here. And so the actual like discrete algorithm before the rejection step is you run k steps, where k is some like parameter I specified from the algorithm of the following like leapfrog integrator. So from your point, you draw a random velocity, you do this business k times, and then you spit out your final point. This particular integrator has like a lot of very nice properties that I'm not going to like go into too much here, but the main thing that you need to know for this talk is that it's like time reversible in the sense that if I have some like starting x v and some like ending x prime v prime, up to signs in the velocity, sort of like running it backwards will give me the same thing as I started with. So there's a nice cancellation in the filter, and you end up just getting a ratio of Hamiltonians. Don't worry about it too much if you haven't seen this stuff before. Okay. So I'm gonna give a quick outline of how we're gonna prove this smallest spectral lower bound first. Just to recall, we're gonna say that the relaxation time is roughly kappa d. Okay. So the first two steps are pretty straightforward. The first one is that we're going to reduce a spectral lower bound to a step size upper bound. So we're going to say that unless your step size is like, if your step size is too small, then you can't mix very quickly in the spectral sense. Okay. The second step is to rule out huge step sizes. So like, there's certain like large ranges of step sizes that we're not going to be able to argue too much about. We're just not going to worry too much about that. So these two steps, I'm just going to outsource the previous work. So the first step is basically taken care of in Sinho and collaborators' work, where they show that under certain like types of constructions, the relaxation time you should think of as basically being inverse to step size. So small step size means large relaxation time. Okay. And for step 2, I'm just basically going to assume that the step size is at most like 1 over kappa log d. You can just do this from the proof of theorem 1, the Gaussian case, which is just kind of explicit calculations. So I'm going to gloss over this. Note that combining these two already shows a relaxation lower bound of like kappa-ish, but we really want to get this d-dependence. So this is our starting point. Okay. So the next step is to argue that when our step size is sufficiently small, I can construct the inverse exponentially sized hard set with the following properties. In this rejection probability calculation, the noise is going to dominate. So basically, like all the other stuff is going to be low order compared to the movement induced by the noise. And then I'm going to argue that from starting in this hard region, most of my velocities that I sample will result in rejection. So the idea is if I initialize you at this like hard region, you just can't get out if the step size is too large. And this will let me prove an upper bound on the step size, which will let me prove a lower bound on the relaxation time. Okay, this is like a high level of how we're going to attack this problem. Cool. So the first step is to argue the following. We're going to decompose the proposal distribution into a random move and a deterministic move. So the random move is just going to sample a random Gaussian vector and add a multiple of it to our current point. And then the rest is just like deterministic. I advance by the gradient. Okay. So formally, the property we're going to use is that if I decompose this like negative log acceptance, you can turn it into a combination of the results of taking that Gaussian step and a bunch of like relatively low order terms for the relevant range of my step size. Okay. So you might ask, like, why would you think to do such a thing? And in hindsight, I think the easiest example is Sinho mentioned in his talk the upper bound on the metropolized random walk, which actually has the same dimension dependence as the smarter Mala algorithm. If you don't care about condition number, you only care about dimension dependence. So if you have like a little bit of experience playing with these like discretized Langevin diffusions, you sort of have this feeling that like really the bottleneck to improving the dimension dependence is this random drift term. And in that sense, it's like it's higher order in this calculation. Okay. And now the upshot of this this above calculation is that it tensorizes. So I can just like make like a hard one-dimensional distribution and like copy it a bunch of times. So this is sort of like the rough strategy. Let's make this a little bit more formal. So what's our goal here? We want to show that like this dominant term of like the effect due to the random move is roughly omega of h kappa d for all the x in my hard set and most choices of random directions g. Right. Just skipping ahead to the punchline, if I were able to show such a statement, note that if I took h to be like substantially larger than 1 over kappa d, then this rejection probability is quite large. In other words, we're rejecting almost all the time. So the point is, if I can show this, then I basically get the result I claimed. Okay, so let's decompose this this first expression a little bit. It turns out you can basically write it as an average of these quadratic forms with second derivatives of f across this line. So let me interpret this formula for you a little bit. X sub s is going to be like a linear interpolation from the starting point x to the point you move to after the random move x sub g. Okay, so x sub 0 is going to be like my starting point, and x sub 1 is going to be like my new point. Sorry for overloading subscripts. Okay, so in one dimension, if I just think of this as like, I replace Hessians with second derivatives everywhere. Sort of, if you just stare at this expression, it suggests that if I want to make it very small, I should just make the second derivative at the starting point large and quickly decrease it along most random trajectories. And if I have that, then this expression is quite small. Okay, this is just by like the imbalance on where it places the mass on the second derivatives. Okay, so it turns out that like basically the entire complexity of this is just showing the expectation of this one-dimensional quantity is small. Because once I have that, I'm just going to like repeat it d times, and then sub-Gaussian concentration will take care of most of the rest of it. There's a little bit of technical care that needs to be done, but that's the high-level difficulty. It's just constructing such a hard one-dimensional example. Okay, so you might already have a guess on like how we're going to do that. Yeah, so basically like we're just going to make the hard region like these like every other periods in some cosine-based construction. And if I start from within these like upper periods, then most random moves, if I pick the scale of the cosine like well enough, will quickly decrease the second derivative. And a few lines of like calculus will show that this has the desired expectation property that we wanted. Okay, and finally to like tie it all together, the hard set of inverse exponentially sized measure is going to be all x, where coordinate-wise it has large cosines, okay? And also coordinate-wise it's not too large. This is just to like control things like gradient regularity and things like that. And it's not too hard to convince yourself by staring at this picture that I can cook up an example where the measure is roughly 2 to the minus d. So that's basically the construction. Okay, and now to turn this spectral lower bound into a mixing time lower bound, I have to do a little bit more work. It turns out that our proof strategy already implies a mixing time lower bound. Oh, yes.
I probably missed something.
Yes.
Because I was distracted. But I thought the lower bounds were for log concave case. How do these cosine functions come into play?
Sorry, so formally the hard function is going to be the sum of a quadratic in the first coordinate. This is to use like the lemma from the Chui et al. Paper to say like the mixing times 1 over h. And then every other coordinate will be this hard one-dimensional function. And in expectation, the rejection probability, if I start coordinate-wise in like these regions, is going to be like h kappa d-ish. And then you can turn this into a high probability bound by like some sub-Gaussian concentration. But okay, formally the hard function is this.
But the instances do end up being log concave.
Yes, this is a log concave function. This is a well-conditioned log concave function.
Okay. Thanks.
I guess you can see from this calculation that the second derivative is bounded between kappa and kappa over 3.
Oh, right.
Okay. To turn this spectral lower bound into a mixing time lower bound, we have to do like a little bit more work. So it turns out that in the large step size regime, theorems 1 and 2 basically already imply mixing time lower bounds, because just recall the flavor of the argument was that from this set, we just can't leave it, right? So you can't mix if you can't leave certain sets. This is like the definition of conductance. But if the step size is small, we need to argue that it requires many steps to move a lot. So here it turns out that you can just kind of like cheat a little bit in the sense that theorems 1 and 2 have a gap. So I can use my step size lower bound from 2 on a instance from 1, and it'll just be like totally overkill. So let me be a little bit more formal about this. So to show a lower bound in the small step size regime, we're going to use a target as a standard d-dimensional Gaussian, so like normal 0 identity. We're just going to make the starting set like x, which is kind of like close to the origin. And we're just going to argue that over roughly kappa d steps, when the step size is like 1 over kappa d, A, the chain never rejects. So basically like all the proposals pass. And B, x doesn't move by too much. So like originally it's like 0.5 root d in radius, now it's like 0.9 root d. And it's not hard to see that like if you only stay within a ball of 0.9 root d, you haven't mixed. Okay, and as I mentioned, to prove that the chain never rejects, we have to use that the step size is like so overkill for Gaussians that like over the course of the entire algorithm, it basically never rejects. Okay, so just to wrap this up, The full proof of theorem 3 has kind of 3 cases. So to rule out very, very large step sizes, we use an explicit Gaussian construction. To rule out intermediate step sizes, we use this cosine-based construction. And then to finally tie it all home and show that very small step sizes can't be used to obtain fast mixing, we use a Gaussian again. So yeah, it's kind of interesting to like maybe remove all this casework and come up with one compelling hard example. But this is sort of like an artifact of how we do things. Okay. So I guess I have a little bit more time to talk about our HMC lower bounds. I'm going to focus on the spectral lower bound. And sort of the first thing you would try if you, the leapfrog discretization is nice in the sense that once you expand out this difference of Hamiltonians, you give this like relatively nice looking expression on the right due to many, like, to me, unexpected cancellations. Okay, and the first thing you would try is you say, okay, this thing in the sum basically looks like that Mala calculation you showed like many slides ago. So why don't I just like repeat the Mala argument k times and then trade a k for a k and then get the same lower bound. So unfortunately, there's some technical difficulty in doing this because you're taking a joint expectation over the entire sum. And we did try this, and you basically it does lead to some mixing time lower bounds, but basically the order of decay of k is more like 1 over k squared. And this sort of we don't know how to get around this, and we actually think it might be like interesting to explore this from the angle of upper bounds. Okay. But taking a slightly different approach, for Gaussians, this entire expression vanishes because, well, if you remember the calculation from like a few slides ago, it's like an integral of a Hessian, and the Hessian is a constant. So this stuff is all like 0. Okay. So the remaining thing to do is argue that there's a certain threshold of step size where above that step size, we can sort of like cheat a little bit, and I'll be like a little more precise what I mean by this. And then below that step size, we're basically back in the case of Mala, where these iterates behave a lot like the Mala iterates. And then I can just apply theorem 1 again. So that's the high level strategy. A little more formally, supposing our negative log density is a quadratic, the first step we do is we just write the coefficients of the HMC iterates as polynomials in the step size and the eigenvalues of A. Okay, so this is like a lot of like messy looking math, but the main punchline is we try to come up with a characterization of these polynomials of these coefficients so that we can kind of trick HMC into doing something very funny. So the idea is we want to design a step size range where these PKs and QKs behave in a weird way. We want PK to be like ±1 and QK to be like 0. So the idea is no matter what random velocity you sample along some coordinate, if I can make it so that this is always 0 and this is always like ±1, you can't leave any symmetric set in that coordinate, and therefore HMC will get stuck. And then below that parameter range, we're going to use the Mala analysis. Okay, so yeah, so I guess the punchline is that HMC is actually doing some kind of funny Chebyshev polynomial stuff behind the scenes. So actually, I'm curious if people know like so when we wrote the paper, I was under the impression that this connection was maybe not known before, but digging a little bit further after talking to some people, it seems that some people in numerical analysis noticed that HMC leapfrog iterates are implicitly implementing some Chebyshev polynomial. I want to like get to the bottom of this source train. So please talk to me if you know about this. But anyways, the point is we can actually characterize these polynomials PK and QK explicitly and say, okay, the first coefficient is related to a Chebyshev polynomial of the first kind, and the second coefficient is related to a Chebyshev polynomial of the second kind. And they have these nice properties that extremal points of the first kind are zeros of the second kind. So I can exactly get the kind of behavior I want. Yeah, it's a bit magical to me, but the point is if the step size is too large, I can like plant a hidden coordinate and make it so that this extremal behavior happens. And if the step size is not so large, then in these coefficient calculations, the first term dominates, and basically I'm back in the Mala regime up to constants. There's a little bit of care that needs to be taken to like make sure the constant here and the constant here match up, but I won't go into that too much. Okay, but this is sort of like the strategy. Cool. As a few parting thoughts, I want to say direct open questions of our work include simplifying our constructions. So many of our constructions are sort of like multi-layered, and we kind of like do different cases to handle different regimes. Like at least aesthetically, it's interesting to see if this is something you can list. Another interesting technical artifact of our analysis is that our exponential lower bounds are actually bottlenecks at 2 to the d. So for these cosine-based constructions, like we kind of rule out warm starts of measure roughly 2 to the d. And this is like kind of inherent because like, you know, cosines, like every other phase is like 2, right? But in fact, a recent upper bound we showed was that you can assume that the condition number is any, if you're only trying to go after rates that scale linearly in kappa, you can show the condition number is like any constant close to 1 that you so desire. So there's actually some like, yeah, these sort of statements are at odds with each other, and it's interesting to see if we can remove this 2 to the d barrier. Yes.
So to be clear, this the precise question here is whether you can do these constructions with 2 to the d replaced by like 1.01 to the d.
Yeah, exactly. Yeah. Okay. Yeah, from an upper bounds perspective, one direction I'm personally quite interested in is that the lower bounds on HMC sort of are very rigid in the sense that they assume fixed step sizes and counts for the HMC algorithm. But in practice, a lot of like these heuristics actually try a bunch of candidate step sizes or a bunch of candidate step counts and then pick one adaptively. So it's interesting to see if we can get stronger upper bounds for these heuristics defying the lower bound constructions. Also, I want to mention that this like k versus k squared gap in proving a mixing time lower bound for HMC, it might be real, and I sort of want to understand if we can capture this effect in the upper bound side. Okay, and finally, on the lower bound side, you know, at this point, we must be sounding like a broken clock, but yeah, anything algorithm agnostic in high dimensions would be super cool. So, okay, thanks so much for coming to my talk, and I wouldn't be doing my my dues as a co-organizer of the complexity of sampling working group if I didn't tell you to also stop by and work on some of these problems. Great.
Thank you, Kevin. So we have a few minutes for questions. Do you have any questions? Yes.
I first want to start with a comment as someone who has thought about lower bounds. Just in defense of your work, it is very hard to derive algorithm-independent lower bounds, and anyone who spends time thinking about it would realize that very quickly, because it's even difficult to figure out what is necessary to generate a sample. But okay, so that part out. I'm wondering, so how far can you push these techniques? So you know, an obvious next thing to try is a lower bound for a metropolized random walk. So what is missing to get that?
Right. So I guess there is an upper bound of D for metropolized random walk, and our proof is kind of showing that D is right. So I guess like the interesting question there would be like, what is the right dependence on kappa? Probably. That one's pretty. Yeah, that's pretty interesting. I haven't thought about that. That's a good question. Yeah, our technique kind of like under the hood is already handling the D dependence of random walks.
Questions?
Can I ask a question?
Yes, please.
Yes.
So there are some of these works trying to establish upper bounds for HMC by using some not a leapfrog integrator, but something more sophisticated. So, I mean, have you thought about proving lower bounds for these?
Yeah, it's interesting. I think so maybe the biggest mismatch in assumptions is just that typically using smarter integrators requires higher derivative bounds. I guess, yeah, I actually have thought about it a little bit, but not very seriously. It'd be interesting, at least like under like the Hessian-Lipschitz assumption, which has been used to get improves upper bounds under a warm start if we can show lower bounds depending on the dimension. So yeah, I think there's this phenomenon that like HMC, if you assume more derivative bounds, then you get like better behavior. It'd be interesting to like understand this curve, if that's kind of what the question is on.
Yeah, but I think if I remember correctly, there was this work by Yingtai Li and Santosh Vampala that they actually only assume first order derivatives, and I mean with this sort of collocation type of integrators. Yeah, so that's in the low accuracy regime. So that has like an inverse poly. It's like not adjusted. So it's right. Yeah, exactly. It's not metropolized. Yeah. So I think the statement is like you get W2 guarantees under no dimension dependence, but like when you try to convert it, you get some dimension dependence. Mm-hmm.
Okay, very good. Thank you, Kevin. And I think let's take the conversation outside. So thank you everyone for attending the first day of the workshop. We'll have a reception today, and thank you, and see you all again tomorrow.